Hello AP Chemistry and welcome to solution formation. So, quick note, please never, ever, ever, ever write as an explanation that like dissolves like, okay? I know actually, I'm pretty sure last year's textbook said that and this year's textbook also says that in there, right? But they are all saying it as a, here is something that might help you better remember, right? But you will never, ever write that as an actual answer, right? In order for one thing to dissolve in another, right, there must be a shared force of attraction, okay? In order for one thing to dissolve in another, there must be a shared force of attraction, right, which goes back to our intermolecular forces, right, with this one being like your asterisk intermolecular force, okay? So like it shows here, right, we have two nonpolar molecules, right, where yes, they are miscible because there's a shared force of attraction, right? Likewise here, two things that are polar, two things capable of hydrogen bonding, right, and ion dipole. Note that this is sort of like a gray area here, right, where hydrogen bonding, things that participate in hydrogen bonding can dissolve with things that are just polar, right? So there doesn't, it's not like there's some line of demarcation here that says polarity ends here, hydrogen bonding starts here, right? So that's a hard place to, you will always have some data or some observations or something to help you frame an answer, okay, with the chemistry that you know. Okay, so things about solution formation. So this is just taking Hess's law and applying it to the concept of solution formation. So we've talked since last year, right, that every single time we break a bond, right, every time we break a bond, which is if we think about it, right, dissolving, and so here obviously no, water molecules don't just part, okay, from one from another, right? Salt particles don't just part one from another and then they all magically intermingle, right? That's obviously not how dissolving actually occurs, right? But we have to have some way to think about it, right? Much like the Born-Haber cycle gives us a way to think about lattice energy, right? And helps us to frame the energetics of ionic compound formation, right? Likewise, that's what this diagram does, okay? If we think about solvent molecules separating, right, and that being an endothermic transition, right, solute molecules have to separate, right, and that's also endothermic, because if I'm going to let one particle interact, if I'm going to let my solute interact with my solvent, that means that we need to create space for those two to do that interacting, right? So, I mean, I feel like that makes sense, right? And then, obviously, when my solute and my solvent particles intermingle and an attraction is established, then energy is released, and that step is going to be exothermic, right? Always, right? These two steps are always endo. This step is always exo. It's just a matter of how endo versus how exo, which gives us determination of the dissolving process being endo or exo for a particular compound, right? And note that just as a other part, right, the difference there, right, from where you start and where you end, right, is your heat of solution, right? Just like when we looked at these diagrams back in chapter 5 and 19. Yeah? Okay. Saturated, unsaturated, supersaturated. So we haven't talked about equilibrium formally yet, but it is very important, right? So let's say we have a spectrum here, right, where this is solubility. That's the solubility of a compound measured in either molarity, right, so moles per liter, or it's often measured in grams per 100 mils, okay? And so that is the solubility limit of a said thing, right? So anytime we are down here, right, this would be our unsaturated, which means that there is no solid in my solution, yes? As in, we don't see the presence of the solid, right? It is 100% dissolved, and in that case, it would be unsaturated, and this technically goes right up here to that solubility limit, right? Then right here, right, at the solubility limit, if we go beyond that, right, this would be our saturated solution. So saturated, right, going back to equilibrium, just means that the rate of the forward process, so the rate of dissolving, right, rate of dissolving is equal to the rate of crystallization, okay? Rate of dissolving is equal to the rate of crystallization, yes? As in, the amount of solid going forward and the amount of solid going backwards is equal, such that there is no net change, right? So macroscopically, nothing's happening. Microscopically, definitely a back and forth constantly happening, but because it's happening at the same rate, macroscopically, we don't observe anything, right? And that would be called saturated. So in order for a solution to actually be saturated, there must be some solid present at the bottom of my beaker or flask or whatever it is that I'm doing my dissolving in. Yeah, does that make sense, right? And then we have supersaturated, which would be a special condition wherein we don't see anything in there, but we are beyond the point of solubility, right? And note that you would have to use special conditions to make that, right? You would have to heat the water or the whole solution, right? And keep adding and dissolving, right? And then you end up with something that's super saturated if you cool it very slowly and do not disturb it, right? But then obviously if you add any disturbance, right? So if you add a crystal of whatever your salt is, right? Or sometimes even if you just get lint or whatever, if you give it any point of crystallization, then it will crystallize. So anyway, just definitions that you ought to know about types of solutions. Solubility in IMFs. So again, right, in order for something to be soluble, there must be a shared force of attraction, right? And so this is just a point of reference. So you're not expected to memorize the formulas for any of the alcohols, but you should be able to, given a table like this, discuss, right, the observations, right? So this says that methanol, not terribly soluble in this, which is a hydrocarbon, which means relatively nonpolar, right? Water, polar, okay? So if we look at this, methanol only has one hydrocarbon group, and then it's got that OH, which is both polar and capable of hydrogen bonding, right? And if we look at this, right, the bigger that nonpolar end becomes, right, because again, thinking about our alcohols, right, we have an H here, and then we have our R group, right, where R is whatever this methyl group is, whatever this hydrocarbon group is, right? The bigger and bigger that R group gets, the less and less polar my molecule gets, yes? The less impact of that hydrogen bonding, right? Because once we start to get to molecules that are, by the time we get to butanol, right? So by the time we get to 4 carbons, that has such a non-polar attribute to it, right? That it's effectively, it's hugely cut the solubility in water, right? It went from being infinitely soluble to being barely soluble to then quickly being essentially insoluble. Yes, does that make sense, right? And then obviously here we see the opposite trend, right? Okay, a couple of other things to think about for solubility, right? For gases, right? Always for gases. If we increase the partial pressure of a gas above the solution, right, we get more dissolving, right? Going back to what equilibrium, right? Equilibrium is restored when the number of molecules leaving, 2, is equal to the number of molecules going back. So again, microscopically, we still have movement in and out. Macroscopically, nothing else changes. Yes? Does that make sense? Okay. What else? Oh, and this other one, this is just about temperature, and this again, something you have enough life experience to tell you that, right? Where if we increase the temperature, on average, things are more soluble, right, with a rare exception. Thank you for listening. Be good. I will see you soon. The next video covers the actual very last tidbit of the chapter where it gets to IMFs and phase change of the unit. All right, thank you for listening. Be good, and I will see you soon. Bye.